NTU World of Wisdom. Welcome to High Impact Thesis. In this podcast, we speak with researchers from various scientific fields to talk about the motivation, goal, and potential impact of their research. We also want to give you a sense of how a PhD is carried out with an emphasis on the PH, the philosophical aspects involved in pursuing a PhD. Welcome to the High Impact Thesis podcast. Today's guest is Mr. Kashyapa Naren Athreyas. Kashyap, thank you very much for being with us today.
Thank you, Chris. Thank you for having me here.
All right. So as we always do on this podcast, we like our guests to feel free. We believe you're the expert on the topic that we're going to talk about today, or the topics we'll cover today. So the questions we have are supposed to be guiding questions, but we want you to explore the vast breadth of the field that you're in. Okay. So to get us started, we'd like to hear from you. What is the short version that you give to someone that you meet transiently if they ask you, what is it that you do, Kashyap?
Okay, yeah, sure, thanks. So basically, when anybody asks me what is my job, nowadays I basically say I am a satellite engineer. So what that basically means is I do a lot of engineering work which goes into the development of satellite. Mm-hmm. So the satellites that I work on, it can be from weather satellites to satellites that pretty much don't do anything. Mm-hmm. But that is up to the person who tells us what kind of satellite he wants. And currently, the main work I do is basically control engineer for the satellite. So the satellite needs to have some kind of control about where it turns, how it turns, at what rate it turns. To, let's say you say that you tell me that you want a picture of Singapore, and the satellite needs to give you a picture of Singapore. So the satellite basically needs to turn from whatever it is looking at to looking at Singapore and take a picture. So basically the system that controls the attitude. So basically in satellite terms, attitude means the orientation. Mm-hmm. In general English, attitude is completely different thing, but when it comes to satellite, attitude means the orientation or angle of the satellite. So we call it attitude control system.
Mm-hmm. I see.
Yeah.
So it's basically about designing control systems for satellites to orient them in a certain direction depending on what application you are.
Yes, exactly.
I see.
That's some truly exciting stuff. Can you tell us a bit about you, the person, so that we get a feel for where you're coming from in a sense? So maybe about your background and how you got here.
Okay, sure. So basically, I'm from India. I studied aerospace engineer for bachelor's. So from that on, I was always more interested in aircrafts, I have to be honest. Mm-hmm. I did aerospace engineer. My thesis in my undergrad was completely about aircrafts. Then somehow I got into doing masters in space science and technology. That is where I was completely exposed to the space science, like outer space, upper atmosphere, or atmosphere in general. And also, when we talk about space, the only way we can study space is by satellites. So we studied a lot about satellites in that. So that is how I got my interest into satellites. Mm-hmm. So that basically opened my idea so that, we always think about, when it comes to satellites, we always just go to the big guys like NASA or ESA but it seems very far away to most of the people. Mm-hmm. Even people who live in America, it is not a common thing to be going and working in those companies. Yeah. But the more you get into it, the more you know that satellite technology and development, it's everywhere. So then I somehow ended up in Singapore for my PhD. Yeah. So in my PhD, I went off a bit from satellite, but in terms of application side. So what I did was I did atmospheric remote sensing techniques and application from satellites during my PhD. So basically sensing atmosphere and modeling atmosphere using satellite data. So I ended up having that coming from an aerospace engineer going into satellite, where I learned a lot about space science and everything and how to build a satellite, from doing PhD in an application side of the satellite.
I see.
And now I've been working in the satellite research center, basically, where I work as systems and control engineer. So most of the time I'm working on developing the control systems and testing the systems and how we are going to do a certain task based on the application in terms of control. So that is how I spend most of the time nowadays. But of course, I'm still have one feet in the atmospheric side, where I do some research about atmosphere.
I see.
But that is not my main job.
I see.
Yeah.
So while we're at the basics of satellites and exploring space using satellites, could you give us, to the people out there who are listening, who, like you said, there is this sense of space being for the big guys like NASA and ESA and so on. Could you give the audience a sense of what has changed? That, right now you are doing space, something that perhaps isn't common in Singapore, but maybe you can give people a sense of what has changed maybe in the last couple of years in terms of satellite development and spacecraft development broadly.
Yeah. So basically, if you compare last 50 years in space technology, right? Previously it was only about the big guys, the space race between Russia, US. Europeans were not even in the race back then, and it was always about who does what first. When it was that kind of mindset, it is all about money, how much money you can put into this to accomplish this. So back then it was insane amount of money was poured into this business to build things. And then somehow in the later years, it started going into a phase where the industry started to care about getting meaningful data. It's not just about exploration anymore. It's about predicting stuff, helping the data that can help our life become better. So that is when Earth observation came into picture. So that is when Earth observation satellites came. So basically that means we observe the Earth from the space to basically get an overview that we don't get on the ground. And so basically we can predict, when we have an overview, we see more things. So that means we also can predict some things, right? So so that is how the industry started to be driven since 80s and 90s. And then once people got to know that satellite is a technology that we can really use to develop weather prediction, and that became a huge thing. So then disaster management came into thing, and then we can evacuate people in time if we know that there is something that is going to happen very soon. So these were becoming a driving element of satellite industry, and the exploration side was just there. It was not the important element of the space industry anymore. It was more about getting some meaningful data and using it for the benefit of human beings. Or animals also have not. Let's say Earth in general. So let's say from then on, it came into one of, then I think at some point there was this International Space Consortium that was made, which allowed some satellite data to be freely available on the internet. So that means any guy, ABC, can go on the internet, get access. It might be limited access, but he or she can get access to this data and do some research. So you can see how things have developed. Previously it was always about the space race. That means it was about military and all that.
Yeah.
Nothing. Then it came like the same guy started to do Earth observation. Then it came into a phase where the data is now available to common man. So once common people started to get idea about, we can do this. So then now if you see, the industry has changed so much. Like high school kids are building satellites.
Yeah.
And like people are like, there's crowdfunding for satellites. There are so many opportunities to build satellites now. So the technology is very handy now. You can just get an article about how to build a satellite, on the internet. It is not even about like, it's the element of complexity is still there, but it is also
much more accessible now.
Yeah, it is much more accessible. So I would say that is the way things have changed over the years.
Nice. Yeah, I think that gives a really good picture of the progress of research into space from across the last decades. All right, so now we would like to move on to more details and specifics about your own research work and what you do on a day-to-day basis.
Okay.
What kind of problems, research problems you are trying to tackle, and then so on. So if you can give us a sense of your own research.
Yeah, sure. So basically, currently I would say most of my work goes into something called mission design of a satellite. So there are two aspects of developing a control system. First part of the project will always be mission design. So what this basically means, like before we decide what we buy. So satellite has a lot of electrical and mechanical components, right? Because it's a real thing.
Yeah.
So before you decide what electrical and what mechanical components do you put inside the satellite, you need to conceptually develop the idea and the proof. It basically proof of concept of what the systems are going to do based on what is needed to do. So let's say I have a customer who comes and tells me, okay, he needs 1 meter resolution pictures from certain orbit. So basically, when satellite goes into orbit, we have different altitudes we can put into based on the application. So usually, I work on the Earth observation satellites. So Earth observation satellites can go anything up from 300 to 900 kilometers. Usually, those are called low Earth orbit satellites. Then there are those special kind of satellites which are called geosynchronous orbit satellites, that is at 36,000 kilometers away from the Earth.
How are these different from the lower orbit satellites?
So basically, I can understand that the concept of distance is getting blurry because there is 500, 900, then 2,000, then 36,000. So when we say geosynchronous orbit satellites, that basically means geosynchronous. It's synchronous to a place in geography. So basically, geosynchronous satellites are not something that you can just decide on your own that you will launch. It is when it's dependent on the country and the size of the country. So a country of a size of USA, it's quite huge. It's a huge country.
Yeah.
So it can have several different geosynchronous satellites looking at it. So geosynchronous means there is Earth, there is, let's say, New York, and this satellite is 36,000 kilometers away from this point.
Mm-hmm.
And as the Earth rotates, this satellite rotates at whatever speed it is necessary to always look at New York.
Okay. So it basically follows the rotation of the Earth.
Yeah, it is synchronous to a geographical location.
Mm-hmm.
So, but if you can imagine an image that is taken from 36,000 kilometers away, will cover a very huge area of Earth.
Yeah, for sure.
So that is why geosynchronous satellites are special in the sense that not everybody gets the permission to launch them, because let's say Singapore launches a geosynchronous, it will get a picture of all these other neighboring countries, which you don't want, which they don't want to give you. Yeah. So that's why the concept of low Earth orbit satellites are there. So basically, when you are just there 500 kilometers, 600 kilometers above Earth, most of the picture, if you just take a very good quality picture, all you can cover is maybe 500 kilometer by 500 max.
I see.
Yeah. So, I mean, on an average.
Yeah.
So, like, coming back to the question, right? So, this is the problem statement, that he wants to take some pictures of Singapore, let's say, from 500 kilometers. So, there are a lot of things that we need to think about. He doesn't say how big the satellite should be. He's a customer. All he cares about is the picture.
Yeah. The end product.
Yeah. He only cares about the end product. But it is, as an engineer, it is our job to optimize the satellite. You don't want to build it too big. If it is too big, that means it's too heavy. That means you use too much power. It also means that you have to pay a lot to the rocket that you are going to put in because it's bigger. So you want to make your satellite as small as possible.
Mm-hmm.
But it should do what it's supposed to do. So that means even before you start building the satellite, there is a lot of calculations that go in the study. So basically, there is power. So we have solar panels on the satellite to give us powers.
Yeah.
How big the solar panels are supposed to be. Like, how many cells inside? What cells? What's the efficiency of the cells? So that is something the power engineer will work on. And similarly, the communication engineer will work on how to deal with the communication aspect of the satellite. And so a control engineer basically has to see, okay, we have to take a picture of Singapore. That means when whatever we are looking at, when it comes to Singapore, the satellite should know that, it's over Singapore. It needs to turn from wherever the camera was looking. It needs to turn to Singapore and take good quality images.
Mm-hmm.
So what does it mean, taking good quality images? That means it cannot be blurry.
Yeah.
So, I mean, we have all taken pictures. We have all taken blurry pictures.
Mm-hmm.
So what does it mean to be not taking blurry pictures or steady hand? So its control system, it's not only just about turning and taking picture. It should maintain the satellite to look at the same space for whatever amount of time that is required to click and process the picture.
Mm-hmm.
So that is called stability of the control system. So one thing about control system is how quickly it can get to the place where we are telling it to go. And the other function is to maintain that stability. We don't need unnecessary jitter. We don't need unnecessary vibrations. When we come there, we don't need the satellite to go back and come back like that. So it's not a good control system. So the control system says, okay, you go there, it should go there and stay there. So two functions. So as a control engineer, we have to design a system which can do this. So we do a lot of calculations, like let's say, what is the atmosphere like outside at the height where the satellite is? What is the power we get at that altitude? Yeah. And what is the gravity pull at that altitude? What is the magnetic field at that altitude? So because all these are forces, if you think about it, all these are forces. We might never think sun rays as a force on Earth because it's too
abundant.
It's too abundant, and it's too, let's say, it doesn't move us. But because there's so many other things that move us here, we don't think about sunlight as a moving force. But when you're up there, sun rays itself, we call it solar pressure, solar radiation pressure. So basically, the pressure that the sun rays impose on the solar panels itself can move the satellite.
Interesting. How does that work? Like how powerful is it to push the satellite?
It's let's say it's one of the weakest. Like comparing gravity and like aerodynamic or magnetic, it is one of the weakest, but it's definitely not something you neglect, especially for big satellites. Small ones you can always neglect because you don't have that much solar panel. Like it's like opening up, like let's say International Space Station, right?
Yeah.
It has solar panels everywhere. The amount of photons that fall onto it create like pretty big pressure on the thing. So that's why they have thrusters to counter that pressure. Yeah. So then there is gravity. So although at 500 kilometers, the gravity is much weaker compared to what we face here, but there is still a pull on the satellite. So, and the magnetic field. So how does the magnetic field affect your control system? Because control system it has a lot of electronics, so it can cause things to move. So we have to think about all these things. We have to calculate in advance, and we have to think about how big or how strong our control system needs to be to overcome all this. So we do all these calculations to make sure whatever we design is going to be enough to do its job at that altitude.
I can see there are a lot of variables.
Yes.
Yeah, there are too many variables to take into consideration when you are designing such a system.
And I might well as add like a lot of variables and a lot of unknown variables. Because it is not something we can just measure whenever we want, just to make sure, it's like this. We always have to rely on some other data or some other person who has done it before or some. So that is these data that I'm talking about is what space science people gather. So my friend Christopher here, he works in ionosphere research. So basically most of the time satellites are flying in ionosphere. So there's ion drag. So something called ion drag. So basically what happens, it's a very cool thing. So what happens as the satellite moves through the ionosphere? Let's say ionosphere is full of charged plasma particles. You can imagine it like this. Let's say you take a comb, rub it on your hair. It develops static charge. So something similar happens to satellite when it moves through the ionosphere. So as it is moving through, all these plasma are colliding on the surface of the satellite. So basically the surface of the satellite is metal. So it is conductive.
Yeah.
So all these charged particles are basically colliding onto this conductive surface. This is something, it's a whole big research on its own called spacecraft charging. So spacecraft develops a potential. So when we talk about electronics, right, the basic concept of electronics works under power of potential difference. we design our electronics to work for certain voltage. That means there is a ground and there is a positive.
Yeah.
So what happens when the spacecraft travels through this? There is it collects all these ions. So that means the outer surface of the spacecraft is charging. Negative or positive, it doesn't matter. It is charging in a way. So there is a potential. So that means either positive part of the spacecraft or the negative part of, so what we call ground, it is different from what we design it to be. So that means your components might fail. It will not work as you expect it to work. So that's a whole another research where people have to maintain, regardless of this charge that it collects on the outside, the inner electronics shouldn't get affected by this.
So how would you go about doing that? Using some isolation? Or?
Yeah, so there are some coatings.
Yeah.
So basically, although you can gather charge, so these coatings, basically it's a paint, but it's what we call it fancifully as coating.
Yeah.
So it is in a way it's like anti-static kind of coat, like anti-thermal kind of coat. So it is. So a lot of research goes into making components, even if somehow spacecraft is developing charge, components will be tested, and it is like some called radiation hardened components. So that means there is another kind where because of the charge there can be some ions that pass through this outer surface of the satellites and go hit the electrical components inside. And when such kind of charge goes into components, it can fail. So that is, they build like these radiation hardened components. So it's a very active field of research. So it's a lot of. I'm not too.
It involves a lot of material science, I think.
Material science, and it's. I would say it's a lot of semiconductor science, like it, because at the core of every electronics is that semiconductor p-n junctions that get altered. So what you want is your p-n junction to be fine.
Right.
So I am not really sure about a lot of things in that science, but they do it, man. So there are a lot of satellites which died because of this very reason, where the components have failed just because of spacecraft charging. So, like satellites which cost millions of dollars have failed because of this.
Problem.
So once it can be a battery connecting circuit. Once that kind of thing is failing, regardless of how good your other things are, it doesn't matter.
That's it. Yeah.
So it is a very risky. I mean, I can understand why back in the day this field was closed to a certain groups of people, because it is a risky field of work.
Yeah.
And there are certain, you cannot call back a satellite to do servicing or anything like that. So once it is done, it's done. And once it fails, it fails. And you only make one of it.
Yeah.
It's not like,
it's very expensive and costly for.
Yeah, it's not like cars, like, you have Suzuki version 1 and we will improve this in Suzuki version 2. We call this back or something like that. So, nothing wrong with Suzuki people.
Yeah.
Can you give us a sense of what you are looking at when you are in space because orientation here on Earth, when I talk about orientation, I have some sort of reference, right?
Yes.
Say I am this, pointing in this direction that we know. In space, what variables are you looking at? How do you determine your orientation there?
Yeah. So basically, once the satellite is launched in space, it's lost. The way it works is, it is on the rocket. attached to some corner of the rocket, and the rocket basically ejects it from the rocket surface, and the satellite is just in a tumbling manner. So it's spinning violently. So basically it takes a while to come down, and why it comes. So this series of operations, it basically works like this. The satellite is off when it's on the rocket. We cannot keep it on the rocket. It is off during the rocket. So once it goes into the space and it detaches from the rocket, so there is certain amount of period where we cannot power on. So these are all programmed in. So it is logically programmed to only turn on after a certain amount of time. And once it turns on, it deploys the solar panels and it starts to charge whenever it can. But it is, as I said, it is spinning. It is still spinning. So what we do is we have this thing called magnetic rods. So the only thing we turn on is the magnetic rods. So once you turn on, so basically it's a coil. You pass current through a coil, it generates a field.
Yeah.
So when there is this field and when there is Earth's magnetic field, what does it do? It aligns.
I see.
So this is how we do the initial control. So because the satellite is completely spinning, you cannot say, you cannot use any advanced control algorithms, because this is the first thing is you need to stabilize yourself first.
Yeah.
So the first, these are the first soldiers that we deploy. So once they align with the Earth's magnetic field, it takes a while for them to do it. So once they align, so now it is still spinning because it is Earth's magnetic field and the magnetic torque rods can only align in 2 axes because the force is only in 2 axes, no E field and H field.
Yeah.
Third axis is free to rotate. So basically it is rotating in the third axis, and we have sensors for identifying different things that we know of. For example, sun, stars, Earth. So these are the common objects that we know of when we do missions for Earth. So basically, sun sensor, what it does, it looks for the sun. So in space, it is much easier to find the sun compared to Earth because everything is dark.
Yeah.
The only bright spot is the sun or the Earth. And it knows the difference between sun and the Earth based on the magnitude of the brightness. The Earth cannot be as bright as the sun.
Yeah. So
it's as simple as that. And when it comes in the field of sun, although it's a point, now you see it's like a point signal. So then it will say, oh, I saw the sun, but it is still spinning. Then you start your control system, which has a set of wheels which start to spin. So the way this works is based on the theory of angular momentum. So conservation of momentum. So conservation of momentum basically says that if momentum is in one direction, the reaction will be in the other direction to conserve. So when you start to spin the wheels to, let's say, the sun sensor just told you that it passed the sun. So what do? You start to spin the wheels. You spin it in a way that it's the opposite direction of what you want the spacecraft to turn. So you spin the wheels in this direction, so the spacecraft will move in this direction to cancel it.
It's similar to the gyroscope.
Yeah, it's the same. It's the same concept. So basically, this is control system in a nutshell.
Yeah. So basically, use this system as an actuator for the control mechanism.
Yes. So, and then you have advanced sensors to have precise. When you say you want, so the sun is a point source, right? So you cannot say, even if you view the sun in the field of the sun sensor, it's a point source. It can be, even if I look at here, I still see the sun.
Yeah.
Even if I'm turning a bit, I still see the sun because it's a point source and it's just one source. So what people cleverly developed back in the 80s, or I think even earlier, is something called a star sensor. We have a lot more stars than sun.
Yeah.
So why don't we use them also to get more reference points to compare with? So what people have done, so basically star sensor is an idea that we have astronomy, right? People have looked at stars and built a database for hundreds of years. So we know which star is where exactly. When, let's say, with reference to pole star, we know exactly where some other star, let's say Vega, is. So in the star sensor, basically it's a camera. It is taking pictures continuously, and we just compare the stars that we see in the database we have, and we just try to identify the patterns by comparing the patterns, or which patterns is which patterns. So you select some stars which are bright enough and just compare the patterns in the database. Just keep checking until you find, okay, this is where you're looking at. So now you have a way to orient yourself in a much more accurate way. So this is how we do when we say high precision imaging. So basically with this star tracker, so star tracker is a system which basically employs star camera and does the processing, the image processing, and basically sends the signal to control system to do whatever that is necessary. So that means now the control system can accurately control the satellite with millimeter level accuracy. So, and maintain the stability based on it. So this is the, I would say, pinnacle of the modern control system for spacecrafts.
I see.
Yeah.
But why would you need to use the stars? Like, why isn't just the sun enough by itself?
Yeah, so basically, sun on its own was always had a limitation that, let's say, sun is in one direction. You have looked at it, and...
Oh yeah, so it still remains within your frame, right?
It is in your frame. Yeah. But let's say once you go out of the frame, you are blank for a lot of time. That is one issue.
Yeah.
But let's say your sun is always in your frame, let's say, but it's just a 1 point. Let's say you have a 720 by 720 pixel camera that is looking at the sun. It's just a 1 point in your camera.
Yeah.
And you are using that as the reference. But if you want millimeter level accuracy, just one reference is not enough.
Yeah.
So that is the main issue.
So it gives you 360 degrees.
Yes.
Of control, and at the same time it gives you more precision.
Yes, because stars are much more closer to each other, and you can have a lot of stars to compare with in each image. Yeah.
All right. Okay. So now let's zoom out a little bit and have a look at this field in general at a high level. So you mentioned one of the problems, one of the challenges is the electrostatic charging of the spacecraft, right?
Yeah.
So are there any similar challenges that you can share with us that you feel are quite important for the further development in this domain?
Yeah, so basically electrostatic charges. So basically the spacecraft charging on space environment is an active field of research. So space environment is always an unpredictable environment, because regardless of how much research that has been done so far, it's not enough. So it's like, how do we even collect the data in space? It's just like singular points very far from each other. We just don't know enough about space. So there are meteorites, like some satellites get hit by meteorites.
Yeah.
And so now it's another, talking about meteorites and getting hit by something, the very active field of research now is something called space debris. And it is not something natural. It is something that we have created, and it's satellites. And it's just another word for satellites. It's called space debris. So basically what this means is these are all dead satellites, not doing anything. But they are just up there floating.
Space junk.
Yeah. So what it basically means that usually satellites back in the day, all of them used to have propulsion. So they would send the satellite up, and then they would deorbit the satellite. So basically bring it back using the propulsion. Final, whatever few fuel you have left out, you just use all of it to bring it back. So, but what happened later in 90s and 2000s were, as I said, the industry grew a lot. More people had access to small money, and more people started to know how to build satellites. So they built a lot of satellites which didn't do much, just to make a name that, oh, we have launched satellites. A lot of people launch satellites. And what they do, they don't have any propulsion system. They are just a box up there, not doing anything, but it can hit something. It can hit a satellite that actually does some work. So this is an active field of research of how to mitigate this problem, because now this has gone to a level where I think United Nations have addressed this issue, that this is an issue that we need to deal with. So basically, and few years ago, some said country launched a missile and blew up their own satellite, and that basically created millions of small flying pieces everywhere, going and hitting other satellites. So a lot of solar panels were destroyed. A lot of some other, let's say, cameras were destroyed by getting it. So, give you a perspective. When I say get hit by things, right? Even if a small piece of glass, when it is traveling at 8 kilometers per second, hits you, your satellite is done. So that is the new issue. So a lot of people are actively planning on how to retrieve this junk. So some, I think even NASA has a program that is going on, which they are building satellites that will go up there and clean up this junk. So basically, few methods that I'm aware of is like cleaning up using magnetic hooks or magnetic sails. So you just go and just collect all of them, like how you throw a net in the lake and just gather all the rubbish.
But first you have to locate them, right?
Yeah, so that's another thing. So there are these huge, radars, let's say, radars or observatories, which are constantly looking for all the things that are there in space. They are tracking all of it. I think some of the radars are very powerful enough to even track the smallest objects. So they know where every satellite is, and they know where every junk is.
I see.
But now that is why they have recently they have, SpaceX, Starlink.
Yeah, I was going to ask you
launched a lot of satellites.
Yeah.
I think 3,000 in the first go, and then few more in the second round. And then, so just last week, there was a close-up on what, I think I forgot the terminology they use. So basically, when one satellite goes in very close to another satellite, so basically within a kilometer. So that's a danger issue. So because of these Starlink's satellites, so it has increased the number of, it's basically traffic. So now the space is full of satellites, and all of them don't know where the other one is coming. These are because completely not planned to
be together in the same environment.
Yeah, they are only planned to be together with the Starlink group of satellites. They haven't considered about the other satellites. So just, I think last week there was a close call with another big satellite, with one of the Starlink satellites. So this is becoming a big issue in space now. And I mean, to be honest, I'm not really sure what the end result will be for this, and how probably we will be going with making satellites to bring all these other satellites down. But SpaceX Starlink has planned to launch 20,000 more satellites into this field. So basically, I'm not sure how that is going to work out.
Yeah, it will be interesting to see how it works out.
Yeah.
Okay.
Can you tell us about space? Tell us a bit about space travel. What with the technologies we have, as you mentioned, this was at the beginning was more of a space race. At that time, it was more about going to the moon, and now I think we're going back to the moon and so on. Could you give us a sense of where we are in terms of the state of technology? What can we do with the technologies we have? Because there are people thinking about going to Mars. There are people thinking about building hotels on the moon and so on. What is, in your opinion, currently technically possible? That's just waiting to happen.
I mean, I am always for space travel, man. Ever since I was a kid, I always thought humans will definitely go into space. It's not only just going into space with massive suits and stuff. It's space travel is something that is going to be a norm in the coming future, because the way we are going, I think we will definitely extinguish Earth. So I'm not sure how, that's a whole another conversation. So we are already looking for other planets to exploit. And I'm not saying that in a bad way. It's just the scientific term, right? And just recently there were these near orbit rocket launches from Virgin Galactic and Blue Origin. So basically, like, bunch of normal people just went into space and came back. They were not astronauts. They were nobodies. I wouldn't say nobodies, but they were definitely not astronauts. So they just came back. So that kind of space travel is what we can expect for maybe next 10 years. The tickets are very expensive now, but I definitely expect in next 10 years, normal people should be able to afford, like, going at least once in
a lifetime.
In a lifetime. and going next step, let's say, have you guys heard about astrobiology? It's a field on basically researching about living matter in space. So how it's not only just about living matter in space, it's about how humans can live in space. So they have done a lot of research on this. So some of the documentaries I've seen. So during my master's, I did have a one-time lecture about astrobiology, which I found quite interesting, but they didn't say much during then. But it's about, like, in case we need to live in space, what our bodies have to adjust to it's not like Earth. Yeah. So our bodies are not really made to go and adjust to Mars. So people have done a lot of weird things, like they these military aircrafts which can simulate zero gravity.
Yeah, I've heard of them.
Yeah, I mean, for like some 20-30 seconds. So these astronauts, they go there. I saw this video. So basically, they try to do sexual poses to like verify the feasibility of having sex in space. And this, I think, has been a good, I mean, it's a very important topic. So it's about, let's say, if in a gravity that is not similar to Earth's gravity, how are we going to do basic stuff that we do on Earth? And it's not just, I mean, we see in the movies like all of them doing crazy stuff, but what we don't see is like, oh, how are you going to chop tomatoes in space? Or how your body will be adjusting to doing those kind of things like that you do here. That's a very interesting topic for me because, I mean, as a common man, we don't really care about doing all what the astronauts are doing.
Yeah.
What we want to know is basically how the life is going to be. So that is something I think it's a interesting thing to keep an eye about.
Yes.
And yeah, I definitely want to see how things turn out as space travel grows. Yeah.
Cool. I mean, I've always thought about a honeymoon on the moon as an idea that's going to be very exciting.
Yeah. You just need to.
It'll be very nice.
I'm not sure what you are going to see there, but
we'll figure it out.
But
I just like the name,
definitely take a lot of the sun lotion.
Right. So,
yeah.
It'd be an interesting
Sunrise.
thing to do, but
yeah, because I'm not sure if the 50++ sunscreen will help there.
Definitely not. Yeah.
I need to go and see.
Yeah.
Okay. So I think that's really it. We want to now end with you as a person. What kind of stuff do you like to do outside of your exciting space things? What hobbies do you have as a regular man on the street?
As a regular man on the street, I do a lot of sports. I'm into volleyball, badminton. I did learn boxing a bit, so every now and then I just go box in the gym when there is nobody.
With your own, like,
just the punching bag.
Okay.
And I meditate. I'm a spiritual person. So, other than that, I like to watch a lot of shows. I like to watch anime.
Yeah.
I like to watch movies. I don't really watch Game of Thrones.
That's
Yeah. So yeah, that's me, man. I'm just having fun. That's it.
Do you feel that to what degree do you feel that your worldview, specifically your research perhaps, has been shaped by the movies? In a way, society shapes movies, but movies also shape what we do as humans. Do you think that has come through in your work at all? Or are they very separate?
It might not be a direct impact, but some movies you watch, like you get inspired and you want to do something meaningful. And sometimes if you look back at your work, and sometimes it's like you see that it's not really meaningful. That happened to me quite a lot during my PhD. It's like I did question a lot of times, like, why am I even doing this? It should be something more meaningful. It's like, this is just waste of taxpayers' money. But it is always, I think, necessary to gather your thoughts, and you can still do something meaningful within what you are doing. It's just a matter of time on how exactly we are doing, like what exactly we need to do. So sometimes it is hard because you're working for somebody and it's not like you can just quit. And I think some people do quit, but I'm not like that. So I think some movies do influence the way you work. Mm-hmm. And maybe some movies, although might not be related to what we work, but some sports movies, for example, definitely I think pump you up to work harder, like to achieve, to be more driven. And I think I like those kind of movies.
Cool.
All right. Thank you, Kashyap. We've really enjoyed the conversation. You've talked to us about controlling satellites and making sure that they point at a specific target if you want to take a picture of something. We've also explored the challenges that are there currently, both specifically in controlling a satellite, but also generally questions of space debris. But it's also exciting to hear that you're confident that space travel is going to happen and on a massive scale, and we look forward to that. So, thank you very much.
Thank you very much for your time.
Thank you, guys. I really appreciate being here. You guys inviting me.
All right.
Anytime.
Goodbye, everyone.
And that is the end of the High Impact Thesis podcast.